Hi everyone. So in the last lecture we have seen what is the importance of network functions and how the stability of the system is directly it is linked with the location of the poles in the S-plane. Okay, right? The importance of our network function we have clearly discussed depending upon the pole location, whether the system is a stable system or unstable. If the poles are lying on the right hand of S-plane or the multiple poles are repeated poles are lying on the imaginary plane, then we can say directly the system is an unstable system, and in the remaining cases the system is a stable system. Okay, in this lecture we will going to see what are the properties a proper driving function or a transfer function have to be satisfied. Means let us consider in the last lecture in the starting lectures we have derived the driving functions and network functions for different network. Let us consider if I given a system, okay, which is having a driving function as s square plus 2s plus 1 divided by s cube plus 4s square plus 1, right? I don't know, see whether the system is a driving function. If I ask you to derive, if I ask you to say whether the system is a driving function or not, okay, then you, by considering these conditions, there are some conditions which have to be satisfied by a driving function, driving point function. If these conditions are satisfied by this function, then it is a driving function, or not. If not, it is not a driving function. So in this lecture we are going to see what are the conditions a function should be satisfied to get to say whether it is a driving function and whether it is not. Okay, whether it is a transfer function or whether it is not. Okay, we will see the conditions which have to be satisfied by a function, right? So first of all, let us see what is meant by a driving function. We have already discussed it, right? A voltage function divided by current with at a same polarity, sorry, at a same port. If you calculate the Laplace transform of voltage to a Laplace transform of current at a same port, then it will give a driving point function, right? If it is a ratio of source current to a source voltage at the same port, then it will give that driving point admittance function. Okay, we will denote the driving point function with z of s, driving point admittance function with y of s. Okay, now at last driving point function we will, can write it as n of s by d of s. So what are the conditions should be satisfied by a proper driving function? Okay, so whether it is a, you can, if you want to say whether it is a driving function or not, so what are the conditions it have to be satisfied, we will see. Okay, so consider, see here, consider this have to be the conditions should it have to be satisfied. Okay, so consider, I'm considering two functions, okay, and I will say, and I will ask you whether this function is a proper driving function or not. Okay, so the first function I'm writing it as s square plus 2s plus 1 divided by s cube plus 4s plus s, sorry, s 4s square plus s. The second function I am writing it as s square plus 5s plus 1 divided by s square, okay, s square, sorry, s cube plus 4s. Okay, these are the two functions, and I am asking you to find whether the two functions are satisfying these properties and whether they are driving functions or not. Okay, so we will see one by one clearly. The first function, okay, the first property, the quotients of the numerator polynomial n of s and the denominator polynomial d of s must be real and positive. See here, what are the quotients here? 1, 2, 1, 1, 4, 1. Here 1, 5, 1, 1, 4. Okay, both first and second are satisfying the first property. Okay, right? You can't say by satisfying the first property itself, you can't say both the functions are driving functions. So you have to see all the 7 conditions and you have to say whether that function is a proper driving function or not. Okay, driving function or not. Okay, the second property, if the poles and zeros are imaginary, then such poles and zeros must be conjugate. Means if a plus ib is a pole, then a minus ib should be the another pole or 0. If ib is a pole, then I minus ib should be the another pole or 0. Okay, now first function, what can you write? The first function you can write it as s plus 1 whole square divided by, what can you write in the denominator? Divided by s into s square plus 4s plus 1. Okay, so s square plus 4s plus 1. So what can you write? S plus 2 minus root 3 into S minus S plus 2 plus root 3. Okay. In the second function, what can you write? S square plus 5s plus 1. Okay. So what can you write here? S plus 0.208 into S plus 4.791 divided by S in S, if I am taking S as common in the denominator, S into S square plus 4s. Okay, S square plus 4s means what I will get? S square plus 4, sorry, S square plus 4. Okay, so what I will get? S plus 2i into S minus 2i. Okay, so see the second property, if the poles are conjugate, see here, poles are conjugate. If 2i is the one of the pole, then minus 2i is another pole. Here, okay, here there are no conjugate poles. So the second property also satisfying by the both the functions. Third function, okay, third property. So third condition, what it is given, the real parts of all the poles and zeros must be negative, or zeros and negative, or zeros, and if real part is 0, then the poles of that zeros pole, then the pole or 0 must be simple. Means what they were giving, the roots, the poles and the real part of all the poles and zeros must be negative. Means all the poles and the negative parts must be zeros. Negative means they have to lie, the poles and the zeros, they have to lie on the left half of S plane. Okay, and if the poles are zeros are lying on the imaginary, means see here, if the real part is 0, okay, if the real part is 0 means if they are lying on the imaginary axis, then the poles or zeros must be simple. See here, what are the zeros here? The zeros here are -1 comma -1, poles are 0 comma -2 root 3, sorry, -2 plus root 3 -2 minus root 3. Here what are the poles here? Zeros here, minus 0.028 minus 4.791. Here the poles are 0 is equal to 0 is equal to minus 2i is equal to plus 2i. Okay, so means what we are getting, all the poles are, first of all the poles and zeros are lying on the left half of S plane, and those poles or zeros which are lying on the imaginary axis, there are simple poles, they are not repeated poles. Okay, repeated poles are not repeated poles which are lying on the imaginary axis we are not getting. We are getting the repeated zeros, but they are not lying on the imaginary. So what is the third condition? Is it is saying all the poles and zeros must be negative, and if they are lying on the imaginary axis, it must be a simple pole or zero. It should be not a repeated pole or zero. Okay, so third condition also satisfying by the both the functions. In fourth thing, see here, if the real part of poles and zeros are 0, the poles must be simple. Okay, here itself we have included, right? Third and fourth, both the statements are same. Fifth statement, there should not be any missing term between the highest and lowest degree in the polynomial of n of s and denominator and d of s, unless all the even or odd terms are missing. See here, means if s square is there, then s power 1 also should be there, s power 0 should be there. If s cube should be if s cube is there, s square should be there, s power 1 should be there, s power 0 should be there. If see s cube is there and s square is missing, and again s power 1 term is there, s power 0 is there, even it is in the numerator or the denominator, then it is not a driving function, unless all even should be all even terms can be absent, all or odd terms can be absent. Means if s cube is there, then s power 1, then it is a proper driving function. If s square is there and s power 0 is there, then it is a proper driving function. But if s cube is there, s power 1 is there, s power 0 is there, then it is not a driving function. So in the C, in the first function, s square, in the denominator s square is there, 2 power s power 1 is there, s power 0 is there. Okay, it's okay. Denominator satisfy the condition, but numerator satisfy the condition. But in the denominator, what are there? See here, s power 3, good, s power 2, s power 1, but s power 0 term is missing, so it is not a driving function. So first, so in the fifth condition is the first function is not satisfying the fifth condition. We will see the second function. The second function, what is there? S square term is there, okay, s power 1 is there, okay, s power 0 is there, okay. In the denominator, s cube is there, yeah, s square is missing and s power 0 is also missing. So the second function, we can say that it is a driving function. We will see the sixth and seventh properties also. The sixth property, what they had given, the degree of the polynomial in the numerator n of s and the denominator d of s should differ by either 0 or 1. See here, okay. So as the fifth condition itself, it is failed by the first function, we are not looking into the first function. Now see the second function, the denominator and the numerator, what is the difference between the degree of the denominator and the numerator? It is 1, okay. So it can be 1 or 0, yes, okay. The term of the lowest degree in n of s and d of s may differ in the degree at most by 1, okay. See, means here s power 0 is there, s power 1 is there. Again the degree, it can be differ mostly by 1, it may be 0 or 1, okay. So the sixth and seventh property also, it is satisfying by the second function. So the second function, what I have given, the second function is a, okay, the second function is a driving function, the first function is not a driving function. So by looking of these 7 properties, we can say whether the function, the given function is a proper driving function or not, okay. So here what they had given, okay, test the following driving functions, okay. Okay, they had given some functions and they were asking whether these functions are a proper driving functions or not, okay. So see here, first we will go one by one. So see here, the first function itself, it is the first condition itself, it is not satisfying the first condition. What is the first condition? The denominator and the numerator, the terminals, the quotients must be positive. Here it is a negative quotient. So the first function, what they had given, the first function, it is not a proper driving function. The second function, see here, okay, the second function, just by looking of the second function, you can say, right, what are the conditions it is not satisfying, right? There should be not missing terms between the highest and the lowest degree. But here see, s power 3, s power 2, s power 1, s power 0. The numerator, all there were no missing terms. But here s power 4, s power 3, s power 2, s power 1 term is missing and s power 0 term, both are missing. So what can we say? The function, the given function is not a driving function. The third function, what they had given, okay, see here, s square, s power 1, s power 0, okay, s power s square plus s power 1 plus s power 0, okay. So it is satisfying all the terms are present in the numerator and the denominator, but just by looking of the whether all the terms are present in the numerator and denominator, you can't say whether it is a driving function. We have to find first poles and zeros of the network, okay. So what they have given, s square plus 3s plus 2, then what we s square plus 3s plus 2, okay. So what we will get, the zeros as in the numerator, we can write it as s plus 1 into s plus 2, okay. In the denominator, what is the given, s square plus 6s plus 2, okay, right. What can we write? We can write it as s plus 3, s plus we can write it as s plus 0.35 into s plus 5.64, okay. If you plot in the s plane, what we will get? We will get the poles as what we will get? We will get the poles as -1, -2. Zeros, what we will get? minus 0.35 is the first pole, at second pole minus 5.64. See, all the poles are lying on the left half of S plane. There were no repeated poles on the JMI axis. There were no missing terms. You can say that the third function is a proper driving function, driving point, okay, impedance or admittance function, anything, okay, it is a proper driving point function. Okay, so a proper driving point function have to satisfy these 6 conditions. Okay, right. In the same way, we have some conditions for the transfer function also. What is transfer function? If you go, if you find the Laplace transform of response to source, when the both response and source you have calculated different ports, then we will call it as a transfer function. These 6 conditions have to satisfy by a proper transfer function. Right, in the poles we have seen in the stability concept only. What we know, the pole should be on the left half of S plane. There should be no repeated poles on the geometric axis. There should not be any poles in the right half of S plane. Okay, all these conditions, again we are considering the same thing. Okay, see here, so see here, these conditions have to be satisfied by the proper transfer function. Okay, what are these functions? We will see the coefficients of n of s and d of s should be positive, right? The same condition as a driving function. Okay, the poles and zeros must be complex and imaginary must be occurred in conjugate. So we know that always if a plus ib or else plus x ix is the pole, one of the pole, or 0, then what are the another pole, a plus ib and minus ix. We know that always the roots will be occurred in the conjugate. Okay, third condition. Okay, the real part of the poles must be negative or 0. If it is 0, then the pole must be simple and including the origin, means the poles must be lie on the left half of S plane. If the poles are lying on the imaginary, there should be, it should be a simple pole, it should not be a repeated pole. If they are a repeated pole, even it is at origin, then it is not a transfer function, it is not a stable system, it is not a, it is a unstable system. Okay, if you consider in, if you speak in terms of stability criteria, then it is an unstable system. Okay, right. Fourth thing, there should be no missing terms between the highest and same properties. Okay, the fourth, fifth, sixth conditions are the same. Okay, if there should be no missing terms between the highest and lowest degree. If there are missing terms, then it should be either all the odd terms should be missed, or either all the even terms should be they can be missing terms. But if there is any missing terms, then it is not a proper transfer function. The fifth condition is we have just discussed now, right? The sixth condition, the degree of the polynomial n of s may be small as 0 independent of the degree of the polynomial of d of s. So either in the denominator, in the numerator it can be 1. Okay, means s power 0 terms can be also present, even though in the denominator we are having s power 6 or s power 5, any terms, but the denominator, in the numerator it can be s power 0 or s power 5, anything. Okay, the denominator means we know that in a driving point function, the difference between the degrees in the numerator and the denominator should be differ by either 0 or 1, but in a transfer function it can be any value. Okay, right. So he had given some transfer functions and they were asking whether this transfer function represent a proper function or not. Okay, test the following represent. Okay, they have given some functions and they are asking whether they are representing a proper transfer function or not. Okay, so in first function what they are given, 3s plus 2 divided by 5s cube plus 4s plus square plus 1. Okay, see here, by looking of the function itself we can say that in the denominator s power 1 term is missing, right? So it is not a proper transfer function. The second term what they were given, they are given 2s square plus 5s plus 1 divided by s plus 4 s plus 7. See, the degree of the numerator is greater than the, here what is the degree of the numerator, it is 2, and the degree of the denominator it is 1. But see, but what we know in condition 6, in the sixth condition what they are given, right, the numerator degree, the degree of the numerator will be less than the degree of the denominator. Okay, but it can be, say, the numerator degree can be 0 or 1 or 2, okay, but always it have to be less than the degree of the denominator. But if it is a driving point function, the degree of the numerator and the degree of the denominator should be differ by 0 or 1, okay, 0 or plus or minus 1, okay, they have to differ by 1. But in the transfer function, always the degree of the numerator should be less than degree of the denominator. It can be differed by 2, it can be differed by 10, it can be differed by 100. It is not the condition we have, but the condition is the numerator degree should be less than the denominator degree. But here the degree of the numerator is greater than the degree of the denominator, so it is not a proper transfer function, okay. In the last thing we are having 1 by s cube plus s square, okay, numerator degree is 0, denominator degree is 3, okay, so numerator degree is less than denominator degree, so we can say the sixth condition is satisfied, okay. See here, s cube plus s square means s square term is missing, s power 0 term is missing, means all the even terms are missing. So the fourth and fifth conditions are also satisfied, right? What are the poles? What we are getting, s square plus 2 means what we will get, s power s equal to 0 is one of the pole, plus root 2j is one of the pole, and minus root 2j is another pole. So all the poles what we are getting on the imaginary axis are the simple poles and they are conjugate, so all the conditions are satisfied by the third function. So the third function is represent a transfer function. The first two functions are not a proper transfer function, okay. So this ends our third chapter, network functions. So it is one of the easiest, not one of the easiest, it is the easiest chapter we have in our whole syllabus. So don't leave this chapter, okay. We are having at most 9 videos and the lecture length also very less. Some videos are having less than 10 minutes also. So don't think we are having 9 lectures, okay. We have very simple lectures, okay. So check the videos repeatedly, and if you are having any problem, okay, contact me, okay, or comment in the comment section. I can explain you clearly, okay. Thank you.